Welcome to day 7 of the Advent of Code. I have to confess it's actually 10th day of December. I'm getting a little bit behind here. Let's go have a look to see what we're up to now. Number 7, bridge repair. Trying to repair it, apparently it broke, Engineers tell you it needs final calibrations, but some young elephants were playing nearby and stole all the operators from their calibration equations. They could finish the calibrations if only someone could determine which test values could possibly be produced by placing any combination of the operators into their calibration equations. Okay, so there, all right. Each line represents a single occasion. The test value appears before the colon. It is your job to determine whether the remaining numbers can be combined with operators to produce the test value. Oh, here we go. And the operators are either plus or times, multiply, and they're evaluated from left to right, no precedence, and the numbers are in the order they're given. Okay, so I guess what we're doing is inserting either a plus or an asterisk in between the numbers. So on that first, they actually got examples down here, okay? So 190, 1019, so if we put a plus between them, we get 29, which isn't right, put a times between them, and we get 190, which is correct, okay? So in that case, here we have 3 numbers, so there's 2 potential operators, so there's 4 configurations of the operators, right? Which is what they say here. There's going to be plus plus, plus times, times, and times plus. Okay, we can do that. The engineers just need the total calibration result, which is the sum of the test values from just the equations that could possibly be true. I think we can do that. So let's wander across to our terminal here. Actually, before we leave it, let's copy that test data in because we know we'll be using it. So copy over to here, nkdir07, cd07, n07.rb. All right, so there's our test data. All we need now is our code. That's the easy part, right? We're going to read in that data and parse it. So the first number on the line is the expected result, and then these are the various numbers that get fed with the operators. So we can just split the line. Basically just pick the numbers out of it, and the first number is the expected value, and then the rest is the rest. How about something like data dot each, so we'll iterate over each line at a time because we don't need more than one line to work on. And again, Copilot detach. Thank you very much. So we'll say the expected, and then all the rest, that star notation is Ruby for collect all the rest and stick them into an array, equals line dot split, and it's going to be on a space or a colon followed by a space, so optional colon and then space. May as well say plus just in case. So that's going to give us all our fields, and then let's map them to integers. So we're just going to do map ampersand colon to I. There we go. And let's just make sure that that actually works by just putting it back out again. So if we output expected and that should be values, shouldn't it? Okay, bring up a terminal. Back up here, let's save it away. Ruby 07. Okay, so 292, 11, 6, 16, 20. All right, so let's think about what we have to do here. Let's choose this first line here. So for this line here, what we're interested in is the 10 and the 19. So let's just make ourselves a little playground up here. So we have the 10 and the 19, and what we want to do is to put in between them either a plus or times. All right. So let's go to the next line here. So now we have, this could be a plus and a plus, or a plus and a times, or a times and a plus, or a times and a times. Okay, so we have two choices at each location. So if we look, okay, yeah, all right, so there's going to be 2 to the n possibilities, where n is the number of gaps, yeah? Oh, I've just had a devilish idea. Okay, so we need to represent that we either have a plus sign or a times at each position, yeah? So we have one or two options. So you know what we do when we have one or two options in computing is we have 0 or 1, right? So we have zeros and ones. But look, here's the thing. If we represent, say, a plus as a 0 and a times as a 1, then that's 0, 0. That's 0, 1. I'm liking this. That's 1, 0. And that's 1, 1. Okay? Which is all of the numbers from 0 to 3, or 0 and 2 to the n minus 1. And this is all of the numbers from 0 to 1, which is 2 to the 0 plus 1. Sorry, 2 to the 1 minus 1. Okay, so what we can do is actually get all the possible combinations by simply adding 1 to a number, right? So in this second case here, we start off with a 0. Then we add 1, and that gives us a 1. We add another 1, and that's 2, which is 1, 0. And then we get 3, which is 1, 1. Cool! So we can actually have combinations by just counting, which makes life easy. Ha ha. So let's try that. Let's try that. So we need to work out how many gaps we have. Let's call it gap count. And that's going to be the number of values we have minus 1, right? All right. And we need to work out, oh, and then we need to set up our bits. And then we need to set up how many bits we're going to be playing with, and that's 2 to the power of gap count minus 1. All right. And now what we're going to do is basically just go through every single possible combination of operators and apply them to our numbers. And that is a classic use of reduce. I mean, if you look at all the examples of reduce and fold and things, they basically show it to you as adding operators between successive elements of the list. So that's what we have to do. We only want to go around the reduce loop and length minus 1 times, because that's how many operators we have. So what we're going to have to do is take the first element off that list of values, okay? So let's just call it, say, result equals values.shift. Yeah. And now we're going to try all of our combinations of bits. So that's what I was talking about, that 0 to 2 to the n minus 1. So 0 dot bits dot each do operator combo. Let's do that. Okay, so now we've got a set of bits telling us what to inject between each one. And now what we're going to do is to go through the values, and we're going to use the various bits in operator combo to inject either a plus or a times between successive values. Let's have the calculated value equals, I'm going to take all of the values and we're going to get both the value and its index. And I'll show you why I want to do that in a second, but it's all to do with the bitmap. And now I'm going to call reduce, because you always have to call reduce. Okay, the initial value we're passing to reduce then will be the first element in the list, which we called result. All right, that's a stupid name for it. Why don't we just call it first? Okay, so that's what we're going to call with our reduce do. And I don't have enough room to put all this in here. I'm going to shrink the font down just a little bit, see if that makes a difference. Okay, I hope you can still read this. So our accumulator, and then the reduce, each time around the loop, we're going to get the value and the index. Okay, so remember the index is the position of the value in our list of values minus 1. So the second value will actually have an index of 0 because we popped the first one. All right. So now I can use the corresponding bit in my operator combo to say, is this a plus or is this a times? So if I do operator combo I, that will give me either 1 or 0, depending on whether it's a plus or a times. So we can do a case on that. When it's 0, then the result of our calculation so far is going to be ACK plus value, else ACK times value. Okay, so that's done our calculation. I guess we could just see what happens. If we just feed in the first of these, yeah, let's that 1019. We can see what happens there. Okay, so let's just output the calculated value, and then here we're not going to read another line, so we're going to break out of our loop. So that's just going to give us the 1019 line. Save that away. How many errors we got in this code? Oh, no, look at that. Woo-hoo. Okay, so the first line is 10 plus 19. The second line is 10 times 19. That's pretty cool. All right. Should we let it run? No, actually, because what we're supposed to be doing is creating a sum of all of the values that match. So we can do if calc equals expected sum plus equals calc end. And then we'll just do put s sum. And going back over to our numbers down here, for the test data, we're expecting to get 3,749. So let's see what happens. Scope. Oh, so we get 7,016. Why do we get a big number like that? Oh. Okay, come back over the description here. See, I've got the description open next to it so I can be reading it at the same time. This number, 3267, has two positions for operators. Of the four possible thingies, two can cause the right side to match. So in this case, what we've done is we've actually added that number in, that 3267. We've added that in twice. So that's why we're seeing a big number, I think. So my guess is if you just break at this point, then we'll only add it in one time. 3749. Excellent. So now you know what we're going to do. We're going to go for the big one, right? A copy. Save that away, down to our terminal. I got a feeling this is going to be a massive big number. Let's have a look. Not bad. Not bad. A lot of zeros in it. So we'll come back over here and we'll tell Advent of Code that that's our guess. Hey, and we were right. Look at that. We are really on a roll here. I'm liking this. Okay, so continue to part 2. Engineers seem concerned. Oh no, total calibration result is nowhere close to being blah, 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 blah. Just then you spot your mistake. Some well-hidden elephants are holding a third type of operator. The concatenation operator combines the digits from its left and its right inputs into a single... Oh Lord, it does it on a string basis. So 12 concatenated with 3, 4, 5 would be 1, 2, 3, 4, 5. So, all right, so that suddenly means that all our clever binary stuff isn't going to work anymore because we have 3 separate operators. I hate them. Okay, I think the overall idea is still valid in that we are interested in the possible combinations of operators. It's just we have to generate all the combinations using 3, not 2. So we're going to have to fall back on a kind of more common expression of that. All right, so let's have a look. I'm actually going to create a new file for this because I think we're going to do quite a bit different than this one. Although I would actually like that top part there, so I think we'll just keep the top part, just the first few lines there. Yank, let's call it 07b.rb. Okay, and we're going to need our data. Which is over here. Go back over to the Advent of Code. Copy that out, paste it in, turn off Copilot. See, I'm learning. Okay, so what we have to do now is to generate combinations of, rather than 0 and 1, it's going to be 0, 1, and 2. Let's think about that. We need to generate all of the possible arrangements, I guess, of length n, where n is the number of gaps. So what does our arrangement have to return? Well, let's look at it for like the case of n equals 1. So when the length is 1, it means we're putting one operator between 2 values. And so we have 3 possible values we're going to put. So we could put a 1, we could put a 0, a 1, or a 2. If we have n equals 2, let's put that here, n equals 1, n equals 2, then our values are going to be, actually I'm not going to bother with the braces because they just get in the way, 0, 0, 0, 1, and 0, 2. And then 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. And then for n equals 3, well, it's going to be 27, and I'm not going to fill them all in, but it's going to be 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 1, 1. Okay, so you remember previously we were using kind of binary counting to do it. Here we're using ternary counting to do it. And in the same way that binary, each bit position, if you go up through the word, each bit position updates from 0 to 1 to 0 at half the rate of the one before it. And here we're doing it at a third of a rate of the one before it. But what that means is that we can actually take, to do n equals 3, for example, what we can do is take the n equals 2 case and iterate over it and insert a 0 in front of them all, then go back and insert a 1 in front of them all, and then go back and insert a 2 in front of them all. And that will generate the n equals 3 values. So the first one here is 0, 0, we put a 0 in front of it. 0, 1, we put a 0 in front of it. 0, 2, we put a 0 in front of it. And then 1, 0 goes to 0, 1, 0. Yeah? And that means we can have recursion. Yay! So, base case here is if n equals 1, let's assume we have a result variable, then result is single element 1, single element 2, single element 3, and then we'll return result. And just because I'm not 100% sure that the little less than operator there actually works the way I think it does, I'm going to save that, bring up a terminal. Oh, look at that. Nice error message. If n equals 1, and I should have used IRB, load 07b to RB, arrangements 1. Good. Okay, so we've got our 3-element array just as we wanted. Cool. So if n is not equal to 1, then we're going to get the n minus 1 case. So let's call it a sub equals n minus 1. And then we're going to say 0 dot dot 2 dot each do n result is going to be n dot concat well, there's a small but finite chance that might work, so we'll go down here, we'll reload it. Arrangements 1 works. 0, 1, 2, I'm not too sure where that 3 came from. Oh, it comes from up here. That should not be 1, 2, 3. That should be 0, 1, 2. 0, 0, 1, 2. Oh, okay, so what we need to do is for each of these guys is we need to get, because these are all going to be sublists, and we're trying to join into the sublists, so we need to flatten the list. So let's see what happens if we do that. Oh, I have a horrible feeling I know what's going on here. Nope, that wasn't it. Oh, sorry. I am a total absolute idiot because I have to go through each of the possible subarrangements, right? So this is nested. I think I don't need that. There we go. 0, 0, 1, 0, 2, 0, 0, 1, 1, 1, 2, 1, 0, 2, 1, 2, 2, 2. And then if we go to 3, if we do arrangements dot length, that should be 27, right? Okay. So it looks like we're now creating the arrangements that we need. Whew. Okay, so back up to the code here. Now we can start applying those arrangements to the data. Okay, so expected values, blah, blah, blah. So we have to have equals values dot shift. And now we're going to look at every single possible arrangement of length gap count. So it's going to be arrangements gap count dot each do and then we can go through the same as we did before. So this will be values dot each with index dot reduce first, do accumulator So now we're going to use the value of arrangement I, case arrangement I, when 0 it's ACK plus value, when 1 it's ACK times value, and when it's 2 we have to do that concatenation, right? So 1 and 3, 4 is going to be the string 1, 2, 3, 4. So the cheapest, easiest, simplest, and probably least efficient way I can think of doing that just right now is to say integer, and then we're just going to convert ACK followed by value to a string. So we're going to convert the two to a string, it concatenates them, and then we're going to run it through integer again to return us back another value. And just because I don't trust myself, I'm just going to put an else clause in here. Bad operator. Okay. So now that's going to add up all of our values. So we should have something like result equals all of those guys. Then if result equals expected Oh, okay. Do we have enough ends? I think so. I guess while we're at it, we may as well just calculate the sum. Wow, look at that. Hang on. So we get 11387 on the test data. So go back over to our, what's his name? 11387, look at that. Okay, so we are correctly applying that 3 operator thing. Let's try it with the real data. Okay, so we'll get our puzzle input. We have what looks like almost 800 or something lines of this stuff. And some of them, how long are they? 1, 2, 3, 4, 8, 9, maybe 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. Okay, so 11 is going to be 3 to the 11, which is roughly 2 to the 17. So that's going to be 128,000 possible combinations. I've got a feeling that this may run pretty damn slow because we're doing absolutely no optimization whatsoever. We're calculating all these things every single time. And this particular little operator here is going to be pretty expensive. But you know what? Let's see. So I am going to save that away. And let's try running it. And my guess is, oh, it's finding stuff. I'll tell you what we're going to do. We're going to stop that, and we're going to instead use time, and that will tell us how much elapsed time it is. And that means you won't have to wait, and I won't have to wait. So I'm going to let this run. Oh, 07B. I'm going to let this run and pause the recording, and when it's finished, I will start the recording back up again. Okay, so we executed in 37 seconds by the looks of it. And we produced an answer. So before we go anywhere else, let's just see whether or not our answer agrees with theirs. Here's part 2. That's a big number. Yay, it's correct. Okay, so we found the correct answer in 37 seconds. This was kind of fun. I liked the first part a lot because we could use that binary number trick. This part is kind of mechanical. I'm not like thrilled with this, but I'm actually going to make it redeem itself, but not in this video. I think what I'm going to do is create a second little video where I try and work out how to get this thing to run just a little bit faster, because I think I can see some ways of doing that. And it just hurts my soul to see code this bad. So I will hang up now, see you for number 8, or see you for 07 Part 2, the Performance Edition. Catch you then. Bye.